The talk is motivated by the ongoing developments in machine learning, which of course are impressive, and sort of like a slice of those impressive developments are also in the multi-agent front, ranging from solving difficult games like Go and poker and diplomacy, to multi-agent interactions like multi-robot interactions, self-driving cars interacting with humans or other self-driving cars and so on and so forth, as well as applications that are not explicitly multi-agent, but where a multi-agent angle allows you to arrive at a good learning outcome, like robustifying neural nets against adversarial attacks and stuff like that. Now, these developments pose a lot of challenges for both machine learning and game theory, and I wanted to talk about them and also share some thoughts about how we're trying to lay some, game theoretic as well as algorithmic foundations for addressing those challenges. But it's a widely open frontier, and I hope that in Nash 100, there's going to be a lot more progress on the topic. All right, so a few observations coming from the practical front. First, if you train a neural net to do something for you, and it finds itself in some strategic situation, it's not necessarily going to develop good strategic thinking. So here you see a video of a Waymo car that is trying to enter a highway in somewhere Silicon Valley, and it's been antagonized by human drivers, so much so that it abandons the attempt and exits the highway and tries again. On the right-hand side, up until, I don't know, the O series of models, GPT was not able to solve tic-tac-toe. It was recommending bad actions. Another thing is that you might have heard of this as well, that neural nets are very sensitive in the inputs, in the perturbations in the input. So while this image is recognized as an airliner by a state-of-the-art image classifier, while this image is recognized correctly as a pig by a state-of-the-art classifier, this is incorrectly recognized as an airliner, despite the fact that these two images are very close to each other. The only change between these two images, which is imperceptible for us humans, but is very much perceptible by the neural net, is that somebody went and added this well-orchestrated, noisy image, multiplied by 5 to the 10 times 10 to the minus 3, and added to the pixels of that image. And the result is like this image that is almost the same, but this completely throws off the classifier.
So there exists one matrix that will make it. It's not just a random matrix.
It's not a random. It's a well-orchestrated. But not necessarily too well orchestrated. Like, I can attack your model, and I can go to Google's model. I mean, assuming your model is decent. And then, take the same attack to Google, and probably it's going to work. So it's not like as fragile. It's not like, I don't need to know the details of your net. And also, I can transfer between nets the attacks. It's interesting that it's translatable. Now, something about the optimization dynamics that has been observed in the multi-agent world, right? So like when you train a single agent to do a good job for you, because we're working with like high-dimensional problems, the algorithm of choice is gradient descent. You just progressively try to improve the loss function, and eventually you settle at a local optimum. The optimization landscape is very complex, so you're not going to get a global optimum. But local optima perform decently in many applications. In the multi-agent world, as we have heard several times during this conference, I don't need non-convexity to throw off the learning dynamics. Like I can get chaos in, 3x3 games or whatever, like George can tell us more about it. But there's something more that goes wrong, okay? So like in nice games, the nice, like normal form games, like the nice games we have been talking about, at the very least, I can run the dynamics and average out the iterates and extract from that a good solution, like a minimax or a coarse correlated equilibrium or a correlated equilibrium. In the multi-agent world, we don't know how to do this. Like, we don't know how to average the iterates or do some post-processing over the iterates to get a decent learning agent that is going to be, competing well against other learning agents in the same environment, right? So it's not just that you have chaos or oscillations or whatever, but also you cannot extract out of the dynamic something, a good solution. So that's challenge number 3. And the last challenge is that, game theory kind of breaks. What I mean by that, so like, kind of like the setting that I want us to be thinking about is that you have n agents. Every agent is choosing some high-dimensional strategy that lives in some compact subset of RD. And they have a very complicated utility function that depends on their own choices and the others. Think like each of them has to set the parameters of a neural net, and these neural nets interact with each other, and out comes some payoffs for the agent. It's a crazy setting. So in particular, the utility, chances are, is not going to be concave or quasi-concave or your favorite variation of concavity. It's going to be a bad function. And when that happens, as you all know, standard notions of equilibrium may fail to exist or might be uncountably infinite. And I'll be more precise what I mean by that. But like, in both cases, either you have non-existence or something unusable because you have a continuously supported equilibrium strategies over these compact spaces, not practically usable. And when this happens, here's the thing. So now the challenge here is normative. Like, we have to design those agents. We have to design the agents and tell them what dynamics to run, so that they arrive someplace in a multi-agent interaction, and it's not clear what is our normative recommendation. So we have to find one that is reasonable. Like, it must exist, it must be easy to represent, and it must be tractable. So these are sort of like the framework, kind of like of this talk. Okay. And I'll tell you some partial progress I've made towards answering those questions or understanding this phenomena, but there's a lot more to do. All right, so the call to action is this. Develop foundations, both mathematical and algorithmic and learning theoretic, for these complicated settings that we don't have good approaches to. Right, so because in the future there's going to be agents interacting with other agents and humans, and they're going to be having complex utility functions and complex policies that they're running, and we need some normative recommendations for like what dynamics that should be running and so on and so forth.
But do you agree there's already a challenge for singular RL with deep networks as the function approximation, right?
That's an example of a non-concave setting, yeah. But at least, like in RL at least has some structure. Then there are other settings with even,
I'm just saying if the big challenges there, these are even harder.
Yeah. All right, so the first thing I want to ask is, why is it that sort of like, while on the left-hand side, gradient descent at least goes to a local opt, on the right-hand side, you have chaos, but more than chaos, you cannot extract good solutions from the dynamics. What is going on? If there's something inherently bad with gradient descent, I want to ask: is there some version of what we're going for here that translates to the multi-agent setting? Right. So over here, again, this is also a problematic setting with bad optimization landscape, but local optima work well empirically, for many problems at least. Is there an analog that we could be looking at here? Because this setting is a fortiori, like harder than that setting, right? So this is the multi-agent version of that setting. So, if we cannot go for global optima there, a fortiori, we shouldn't be thinking about global optima here either. So I want to ask these questions, but let's take a step back and remind ourselves what we know and what we don't know. So here's like in my setting, and agents choosing strategies in compact spaces, non-concave utility functions. What do we know? Okay, so a Nash would be let me not call it pure or mixed. A Nash is a selection of strategy for every player so that nobody can deviate, right? This, yeah.
Just a question. But in economics, it's been understood for a long time that a bunch of well-behaved, rational people behave like nothing.
Yes.
Some.
Behave like nothing.
There are no restrictions.
No restrictions, yeah, but again, here we have, yeah.
In some sense, the problem that you're talking about, no?
Not exactly, right? Because as I said earlier, here we design those agents, right? So I want to design my two neural nets that are going to be talking to each other, or my self-driving cars that are running their policies.
You're going to pick the behavior of every agent
against the other agent.
Yes, so that they look like two people playing to end.
So that a good, they convert to some behavior that is good. That, they're, right? So in any event, so this is a very basic solution concept. As you all know, unless the utilities are concave, it's not going to exist. But, we can convexify the setting, right? We can think about, distributions over these compact spaces, so that under the product measure, the same inequality is going to be holding for some selection of product measure. And also, we can even take a correlated measure, right? Like a coarse correlated equilibrium or correlated equilibrium. And this thing does exist, okay? So this thing does exist pretty generally, as you all know. Problem is that it will be, in general, continuously supported over these compact spaces. And that's just not a practical solution, right? I mean, it's hard to think about how I'm going to represent a distribution over neural nets, each of which have 1 million parameters, okay? So it's...
If you find the extreme point, your extreme point, it will be probably found as a supporter or something, or approximate. So,
I mean, there are games that where you cannot do this partification, you agree? There are games that require me to use arbitrarily large supports for the equilibrium.
Is in your setting UI continuous?
For now, it's continuous.
Okay.
Yeah, in general, it may even be discontinuous, but even under continuity, this is the picture. Yeah. Okay, so what do you want to do? So the first thing I want to consider is, as I was saying earlier, is there a version of local optimum that I can generalize from the single agent world into this world? All right? This would sound like what generalization of local optimum is. A local Nash equilibrium is a collection of strategies for these neural nets, so that every neural net is locally optimal, and I have to define what I mean by locally optimal, but locally optimal against the other neural nets. If there's no other neural net, it will be the traditional local optimum that deep learning people go for. This is a generalization of that. Now, depending on what you choose for local optimum, this thing may or may not exist. And as it turns out, okay, so you can choose it to be a first order local optimum, a second order local optimum, an nth order local optimum. The higher you go, the tighter the solution concept becomes towards a global optimum. Some place is going to break. And it breaks at the level 1 to 2, okay? So if you choose local optimum to be first order local optimum, this thing will exist, despite the non-concavities. But if you go to 2, you're done. And there are very simple examples that break the existence for second order local optimum.
sorry, what's second means all the gradients are 0.
Let me show first, and then you ask me what is second order. So first is this. First order local Nash would be so for every player, if they were to look at their gradient with respect to their own strategy, given what other people is doing, and try to do a step, and of course project back to the constraint set, they don't move. So first order deviations didn't help. That's what a first order local optimum is. Second order is, I'll do a second order approximation to my function at where I'm standing, where we're all standing. I'll do a second order approximation of my function with respect to my own strategy. I'm going to optimize that and try to go there constrained by the strategy without going, of course, stepping out of my strategy set. That's second order, and so on and so forth. This is the only thing that I know in this spirit exists. Second order breaks existence already.
So a saddle point might be first order, but not second order.
Correct. But I have more than saddle points here because you can be on the boundary and point out. Yep. Yep. Exactly. Yes.
And you said before something that I don't understand.
Yeah.
That you take first order, second order, third order, infinite order.
Yeah.
And that is a global optimum. Why? I don't understand.
Okay, assuming you give me Taylor. If you don't give me like that, it's an analytical functions. Okay.
I will give you that with this analytic. I will give you C infinity. That would be an infinite order local optimum, right?
Okay, whatever this process converges, like whenever this process, like, it converges to the, it doesn't matter, but yes. Okay.
You sign x plus x.
Let's not be pedantic right now. We all understand each other, so, okay, so we understand each other, so it's okay. Okay, so, and in particular, I mean, this notion has also the thing that, it does capture what people in practice do. I mean, people in practice in multi-agent learning, they're running gradient descent updates, and this is the fixed point of the gradient descent updates. Of course it's going to exist. It's a fixed point. In fact, as it turns out, it is exactly a fixed point. So the problem is identified with Stratis Koulakis, who's sitting up there, and Manolis Zampetakis, who was also mentioned earlier in some other talk. Unfortunately, this thing exists, so we resurrect its existence, but it's intractable. There's no, even in zero-sum games, even if you have two players and the game is zero-sum, if the utilities are non-concave, the problem is intractable. Namely, it takes exponentially many queries, exponentially many steps to queries to the utility function to get there. And if you have white box access to the utility function, it's PPD hard. So we have partial success here, right? So we resurrected existence, but we have intractability. And what I want to do is I want to correct for that. So I want to ask, okay, so, like taking, like this Nash equilibrium that doesn't exist and turning it into a local version, resurrected existence, but didn't quite meet the goal of being tractable. Can I play with these notions and get a local version of them that actually is both exist and is tractable? And of course, I'm going to go with coarse correlated because, this would break even for concave games. It's PPD hard for concave games, so let alone. So some local version of this is what I'm looking for that is tractable. Does it exist? Right, so I want to take a notion, a concept that is guaranteed to exist, but might have continuous support, continually uncountable infinite support, and turn it into a local version that is both tractable and has finite support, by guaranteed to have those. So let's try to do that. Okay, again, this is the concept that I want to relax. And I guess this second bullet is for different audiences, but this is an interpretation of what coarse correlated equilibria are. I want that, on average, the strategy given to me by the joint distribution is optimal against my posterior given that, right? Like if it was for all recommendations, it would be correlated. This is on average. That's because it's called coarse correlated. What would be a local version of that? Guess what it would be. I'm going to go and change this adjective to local optimum, okay? Okay, so it's locally optimal, okay? And of course, we have to all to decide what local optimum means, and we have many versions in the paper. Here is one version, that we have other versions. Generally speaking, it is defined in terms of what is called phi regret, like some kind of local swap regret. But here is a version. I want that for every player and for every alternative strategy they can think of, that their average utility, if they follow the recommendation and everybody else follows the recommendation, is essentially as good as if they were to jiggle the recommendation locally towards this North Star, this xi. And this delta squared here is the right error because I'm looking at first order notion. So I want that the possible improvement from that to be lower order. Like I want it to be, I allow like them to explore a delta step towards this North Star, okay? In principle, I mean, they can improve in principle, but I don't want them to be able to improve too much. Like I want that on average, the gradient is 0. This is what I'm looking for. Now this generalizes, local Nash that I defined in the previous slide. It generalizes also coarse correlated equilibrium, and it's guaranteed to exist. What I'm happy about is that it can be computed efficiently using gradient descent. Right? So this is the best I can currently deliver that meets all the desiderata, like existence and tractability. So this scales nicely in the dimension. The support is polynomial in the dimension.
How about dropping coarse? Can you do it?
For C,
With the same machinery, exactly.
yeah, so we have, so I guess, no, I mean, so in the paper we explore, this is a phi regret notion, where I'm only constraining the set of swap functions to be of this form. And in the paper we also consider other ones, like, like pushing towards the same fixed direction, and some other local ones. But this has to be local. If you allow me to consider global, of course, deviations, that's back to CE, right? So,
I'm saying,
yeah.
But put the conditions for correlated equilibrium instead of coarse. That's all.
Conditional
xi. That's the only difference.
I don't know. So this is close to that, but not exactly, yeah. Yeah. Good. So that's example number 3 that I wanted to mention. Challenge number 3. Okay, so now I'm going to move away from even having compact strategy sets. Okay, so like in principle, I mean, you have an agent you want to design for some scenario. You want to design a program that a Turing machine for this agent to use that does well. And you have a game where there is an enumeration of all possible Turing machines on one side, and an enumeration of Turing machines on the other side, and you want to play that game. How about this game? This is non-compact anymore. So things are going to be difficult, right? How do you resurrect equilibrium existence there? Okay, so that's the question I want to ask now. Well, situations can be pretty bad even for trivial games. Okay, so like this is a non-compact game played over the integers. So 2 players choose integers. Whoever picks the larger number wins. It's a zero-sum game. And I break ties in favor of the purple player. Okay, so this game has no Nash equilibrium. I hope you can see that. Whatever Sergio's distribution is, I will, push my support to dominate Sergio, and then he will push his, and we're going to chase each other to infinity. Okay, so obviously it's not going to have any nice equilibrium. But what if we exclude this game from being a sub-game of our game? What if this game does not exist as a sub-matrix inside our game? Right, so let's consider a game. For now, zero-sum. I will generalize later. And also for now, all the entries are plus or minus 1. It's an infinite matrix. I try to find the biggest submatrix such that if I permute rows and columns, I see this structure. So suppose, like the best I could do could not deliver an infinite copy of the guess, but it's a finite such submatrix. Then Bernard says we're good, and indeed there's a theorem by Haneke, Livni, and Moran from a few years ago saying that if your infinite plus or minus 1 game does not have an infinite copy of this thing inside it, then you have equilibria. You have minimax. That's pretty cool. Who was? I see, okay. So we extended it in a different way. We wanted to do real-valued games and also multiplayer games like coarse-correlated equilibria, and we can do all that. So let me tell you the real-valued, the analog for real values, and there is an analog for coarse-correlated equilibria for multiplayer games. So for real-valued games, what I'm going to try to do is I'm going to try to find a submatrix, the biggest submatrix I can come up with, such that for some theta, I have a gap between the entries below and above the diagonal, a gap of epsilon. And the theorem is that for any epsilon, like if for some epsilon, you cannot find an infinite such copy for any theta inside your game, then you will have a minimax equilibrium, an approximate minimax equilibrium, an epsilon approximate, times some constant. So if you can do it for 0.1, you're going to get something there, 0.2 or whatever. If you can do it for 0.01, you're going to get it approximation for C is a universal constant. It's order, like I removed order to not. It's just 100. I don't know. It's some fixed constant that doesn't depend on anything else. If you give me all payoffs are say or scale them down doesn't. Yeah. Now, here's the thing that I wanted to remark that I think is really beautiful and really cool. And where is Christos? Oh, here there it is. Yeah, we're wrapping our heads around what it means. Okay, so the cool thing is that to prove these theorems, we don't use Brouwer, we use Ramsey's theorem. Okay, that says that like a large enough graph either has a size n graph either has a log and clique, log and people who all know each other, or log and people so that nobody knows each other. So this is Ramsey theorem, and there are generalizations for of that. But point is, to prove this existence theorem, we don't do topology. We do Ramsey, and we want to understand. As you know, we're fixated in defining complexity classes and understanding how they all fit together. So we're trying to understand what this means in the context of PPAD and CLS and TFNP and fixed P and above.
Get rid of this kind of submetrics, then you don't need fixed points.
So how it works? Okay, so here's the rough argument, in fact, to connect to Rahul's talk of how this is proven. So you imagine running the algorithm he was talking about, PSRO, on this game. The challenge game. You're given a game. You try to solve it. The double oracle algorithm, like this. You start with like a 3x3 game. You solve it. You ask player 1 to try to do better than his minimax strategy. You ask the other player to do better than his maximin. You keep going. You want to show that this converges. So basically what you show is that if you fail to converge, you can create, by Ramsey, you can read out of the dynamics arbitrarily large copies of like a game like this. This is how you use Ramsey. It's by contradiction. You say like, here's an algorithm. Suppose it never stops. I can look at the dynamics and extract from them arbitrarily large copies of these structures. Last kind of like direction and more in the creative and fun place. Combining generative AI like GPT or Stable Diffusion or models like that understand and can generate interesting data modalities. Combine them with game theory to address settings where text or other data play a crucial role. Okay, so what I mean by that, games where language, for example, is input or output of strategies, like in games that involve chip talk, like diplomacy, or in games where like agents interact within an environment where things are written on the wall or whatever. So situations where like you want to design agents that use language and condition their strategy on their actions, the discrete actions on language, and also know how to chip talk with other agents and stuff like that. So there's a great progress in that direction in the game of diplomacy, where they use versions of GPT together with reinforcement learning to get superhuman agents that play diplomacy. Use Gen AI, combine Gen AI to improve the efficiency of an institution. In some recent kind of like a paper that I wrote with my postdoc Yannis Daras and some undergrads, we thought about what happens in auctions when you're given access to Gen AI that can generate on the spot for you whatever banner you want to show depending on who won the auction. And in particular, you want many bidders to be able to win the auction. So here's some examples of like using an algorithm. Here is like Gatorade and North Face are competing to show their ad to somebody, a banner. Like in New York Times, there's a banner that is being sold, Gatorade and also North Face that are competing to get that ad. Like in the past, like without Gen AI, either Gatorade or North Face would win the banner ad, and they would each show a pre-computed image to the reader of New York Times. Now you can have them both win, unless like the other company is not offensive for you, right? I mean, okay, there are complementarities and things like that, but like both of them can win. And here, I mean, like I'm showing you examples of like images that algorithms generate on the spot, like where, here, like only Gatorade won, so you don't see any North Face written anywhere. Here, it's sort of like mostly Gatorade, but there is the resolution isn't great, but you can see, North Face. I can't see anything, but North Face and so on and so forth. Okay, North Face, little Gatorade, and only North Face, like with Greek letters and stuff like that. So there's like a lot of creative things you can do, and you can show that this improves the efficiency of, if I'm Google and I'm selling a bunch of banner ads, being able to combine advertisers.
Just one ad is everything.
Unless you don't want to combine P and NP, right? So in the same ad. And finally, and like very closely related to Rahul's talk, understand games that are described in natural language. Like in many situations, games, the interactions between players are inherently given to you in natural language. And you can use the ability of these algorithms to read big corpuses of text and also use their world knowledge to help you understand the situation at hand. In a paper that George, Christos, and other people wrote for NeurIP's creative track, we tried to analyze Romeo and Juliet using this approach, okay, to basically come up with measures of combined sort of like LLMs and game theory to understand the dilemmas that are faced by characters in Romeo and Juliet, and sort of like build an extensive form game for like the interaction between the characters, and sort of understand, sort of like look at the storyline versus, like the equilibrium strategies, and understand kind of like as the story evolves, how characters' decisions influence their fortunes, okay? And I'm not going to say too much about it, but the point here is like we want to use game theory because, like characters make choices, and those choices influence their fortunes, okay? And you don't want to plot what happens only on the storyline, right? Because what makes a story tragic, and that's sort of like our innovation compared to previous work in the previous, let's say, okay, I'm very small to analyze Romeo and Juliet, okay? So, but like, if I try to analyze it using analytical tools, okay, our point here is that you shouldn't just be looking at the storyline and plot on the storyline how the fortunes of people fluctuate. But what makes a person tragic is that the choice they didn't make and chose something else, that counterfactual future might have been better, and so on and so forth. So like, we really want to understand the junction points in the story and nature and what games it plays, and sort of like understand a literary text from this point of view. And of course, because it's a big book, and I haven't read it, I can ask LLM to help me kind of like help me, okay? Help me build the extensive form game. So this is what we did. We asked, okay, like, how many, to list, like a bunch of options that Juliet has, one that agrees more with her family, and one that, and so on and so forth. So we asked GPT to help us with things, analyze probabilities of events that have to do with the technology, like, if Juliet sends a secret message to Romeo, what's the probability given the technology of the era to reach Romeo, and so on and so forth. So long story short, we can build a game, plug it into Gambit. I think we cite you, I'm not sure. If we don't cite you, it's his fault. Find the equilibrium of the game, and sort of like, let's focus on this graph, plot along the points of, where, in this extensive form game that people make decisions or nature makes decisions, kind of like plot, kind of like the expected payoffs in the subtree rooted there, and, the both the expected value and the variance, and kind of like look at this shape of the story to try to understand what makes characters tragic with the choices that they make, okay? That's all. Thank you. That
should be a tragedy, right?
Oh, I see. Yeah, it was. Yeah, it was. There was a big variance that looked like things may look up well for the agents, and like it crashed, right? So in our game model, it kind of like things started looking up, but there is some variance, and and then it crashes, and
Right, and any other questions for Kostis before we finish?
I have a question.
Okay,
I want to return to your earlier question. Thank you.
yeah.
So how should we teach AIs to behave in a multi-agent world? Like maybe, is there any meta lesson or meta intuition?
It's very. I mean, it's a very broad question. Yeah. I mean.
Let me try to make it a bit more precise.
Yeah.
Should we actually even make them strategic?
I mean, it depends on the situation, right? I mean, like, these are agents that are supposed to be acting in the world, and they need some guidance for how to act. And, obviously, the standard approach is to assign that, give them some utilities, and have them optimize them. And we can decide how much altruism to give them and how much personal utilities to give them. And I think all these choices obviously will affect the outcome. Like, like in a future with a lot of self-driving cars, for example, I would like to be able to coordinate the self-driving cars. Also, what I would like to do is I would like to be running markets in the cities of Cambridge, where sort of like, like my self-driving car, because I'm always late, can pay other drivers to, get, green light on the traffic light, so that, so institutions that we can build around our AIs can improve the efficiency of the setting. And communication, as well as altruism incorporating their utilities, are all important things, right? Of course, things can be hacked. These are still, software things, and people can hack them and do all sorts of things they want. So then you have to decide how to allocate responsibility and so on and so forth. So it's a big question.
So you discussed the efficiency of institutions, and you gave the example of an ad or driving in the city. It seems that once we need to specify the preferences, that's going to be a big object, because there are so right?
That is a great question. I think, in fact, it reminds me that one direction that I find very important to add in this list here is using LLMs to try to understand human preferences. And language is powerful. Like if I ask you, hey, can you describe your restaurant preferences? You can say, look, I like, like Mediterranean places, I'm just guessing, formal settings and this and that. And your answer carries a lot of information. While if I ask you, hey, do you like, like this restaurant? You say, 3 stars. And how about this restaurant? And So language also can be very helpful to understand people's preferences.
In this world, I'm glad you returned to this slide, because I was thinking when you wrote up the efficiency of the institution, of course, another goal that we often write about in economics is the equity of an institution or the fairness of an institution. So how would we expect to adjudicate those kinds of things in this world?
First, to be clear, I'm not going to adjudicate them, but like, yeah, I mean, like, that's a fourth, fifth, whatever bullet here, right? So like, and that has to do a lot with alignment. I think it's like economic ideas can be very important to provide guidance for how you align models. As you know, a GPT model trained on the web, make certain predictions, but before it's actually launched, there is an RLHF, an alignment phase, that a fine-tuning phase that aligns it with human preferences. But the way this alignment happens is, you ask humans, hey, here's a question, here are two possible answers, which one you prefer? You ask humans 30,000 questions of this type, and then you fine-tune the model to prefer the answers preferred by humans. But the assumption there is that, like, all humans are homogeneous. Like, the moment you frame it this way, humans are homogeneous. But, economics, we have a lot of other tools. You have a lot of, and I'm riding along. But to think about fairness and, how to combine, different utilities to arrive at more fair solutions. So these ideas can be incorporated in the way we align models as well. So that's there's just a lot of opportunities here for economics to inform how we train these agents.
Okay. Emmanuel has a question.
I can also speak out loud.
Yes, speak loud.
Thank you for the talk. We've listened to a lot of talks today about dynamics in games and how complicated they can be. I tend to believe maybe that's wrong, that humans don't get that complicated behavior when they're learning in games. With LLMs coming up, do you think they could help stabilize learning? Would they make things more chaotic?
A great question. The only thing I'm going to say, not to avoid a very long answer, is that, for example, like another way you might want to use an LLM is for online moderation. Like the moment we align a model to sort of like understand, the various objectives that might exist on a topic, you can launch those algorithms in online fora and, mediate or avoid sort of like polarization, but so there are opportunities there as well, where or self-driving cars, maybe stabilizing traffic on the road and things like that. So there's a lot of potential.
Right. Shall we take one more question? Go on.
Thank you, Kostis, for this great presentation. Question: do you think that the builder of LLMs will try, once they become popular, people will use ChatGPT, but then ChatGPT can get money because they can influence our decisions. They can. What do you think about this? Then it will be a strategic answer of ChatGPT.
Your question is, yeah. So can you repeat? Yeah.
So it's also game theory.
Yeah,
LLMs will also become clever and may manipulate our decisions and, and our opinions, political opinions.
Yeah, I think I think this is a multifaceted question. I'll mention one direction on which I have written a paper, but there's a lot of other things to do there. So if I know that you're using GPT to make decisions, I can exploit you. And we can have, and that relates to Jeff as well. I wanted to ask Jeff, I don't know if he's still here, but you can try to control the other agent. Like if I know your update dynamics, I can feed you things that will make you arrive at the outcome that I want, right? So I'm interacting with somebody on an online dating app, and I know that because they're getting a lot of inbounds. I know they're using an LLM to answer the messages. If I know they're using GPT, I can make the LLM agree to go on a date with me, right? So you get these types of scenarios. So then you have to ask yourself, how do you protect against that and things like that. So.
Yeah, we'll take one more question from Bernard.
Not for the purpose of having the last word, but maybe. AlphaGo or AlphaZero is trained on huge amounts of data in an antagonistic setting because you can generate this data.
Correct. You have a simulator, yeah.
We have also economic models that generate, in principle, also unlimited amount of data. I mean, because 100,000 humans is a lot, is very costly, but I mean, this is artificial data that you can generate arbitrarily. But then there is not an easy benchmark because, I mean, how to beat chess, it's easy to say because you play a chess player, but economic models have equilibria and so on. Do you see a great potential in these synthetic data?
Synthetic data?
Generated from economic models, from mathematical models that in
So I think my go-to approach every time when I want to build a sophisticated agent is not, it ends up not being necessary for AlphaGo, but it was a good start for AlphaGo. You want to have a good warm start, like in the game of diplomacy as well. Like you find an online forum where humans play diplomacy. You see what they're doing. The first thing you do is you do imitation learning, behavior cloning. Now you have a decent agent. That's not going to be a good agent, okay? By the way, like tic-tac-toe that I showed earlier is an example. There are tic-tac-toe games on the internet. GPT saw them. It's not good, but typically, it's a good warm start, and then you build on that. Sometimes you don't even want to go too far away because then humans understand you're a bot, and then they, like in diplomacy, like in a pricing situation, right? If I understand my competitor is using a bot to update their prices, maybe I can try to manipulate them to run them out of budget, and then I'm free to, I'm on my own. So it's a bit of a delicate thing. Yeah, in economic situations, I can imagine things like that, where you want to warm start your agent around economically reasonable behaviors, and then kind of explore around it. So there is definitely a lot of value in a warm start. Okay, so in AlphaGo, in AlphaZero is not used. They do everything from scratch, but in AlphaGo they did use it, and it was a good warm start.
Okay, thanks, Kostis.
Thank you.
I'm supposed to make a few...